This lecture is in continuation to our lecture number 1. I know this lecture has come up a little late. It's because I just wanted to cover up as much as possible, which would have given me much more morale boost that yes, I'm covering it up. Now, this is an extension to the part in which we discussed about the domain, the range, the ordered pair, the relations, the functions, etc. Now, while we are talking about a particular function, then describing a function needs certain rules. Obviously, you're well acquainted with these rules. These rules are nothing but they are simple equations as stated here, right? Now, describing a function by an equation, they are basically rules, right? Now, what does these rules do? These rules talk about that for each x value, what is its corresponding y value, right? That means while we are performing the mapping of our domain with that of the range, because in a particular ordered pair, what are the things that we do have? We have x comma y. That means x is the domain and y is the range, right? The sequence of the y that we do get, from a series of ordered pairs like x1 y1 x2 y2 x3 y3 etc. From here, the number of y's and the number of x's that we do get, they correspond to the domain as well as to that of the range, right? Now, even though we know the basic definition of the function that for any particular x value there should be only one y value, right? Or in much more lucid fashion, we can even say that we can have similar y values or different y values, but we can never have a same x value for a corresponding set of ordered pairs, right? So now here in this case of the rule that we do have, let's say we have a simple rule for mapping the x values with that of the y values. We have a relation, that means a rule, y equal to x plus 1, right? That means for every x value we do have the y incremented. For every x value we have a y value which is a 1 increment of the x value, right? So that requires a choice of an x in the domain. If I put up the x as 2, let's say I'm taking up the x value as 2, then what is the thing that I'll be getting for y value? So if I'm taking up x as 2, I'll be getting y as x plus of 1. That means if I'm having x equal to 2, I'll be having y equal to 3. Now if I am having x equal to 3, I'll be having y equal to 4. If I'll be having x equal to 4, I'll be having y equal to 5. So now this arrow states that we are mapping the domain with the range. We are mapping the domain with the range. We are mapping again the domain with the range, right? Now, even though we do follow certain rules, as stated here, but there are certain restrictions, constraints for the domains of the functions, right? How are we going to put up these restrictions or the constraints? Now, let us first take about let us first consider what these restrictions are and what is the necessity of these restrictions. Unless otherwise indicated, in general, we can consider that domain of a function is assumed to be the largest possible set of real numbers, right? Unless it is stated in any ordered pair or in any function or in any relation that turns out to be a function, we can say that the domain of a function is the largest possible set of real numbers. Now, if this is true, then the domain of y will be stated by a rule which is given here, right? It is also a set of all real numbers. Then the restriction that is to be put up here is, does this relation holds true for all set of real numbers? No, except for plus minus 2. Why? Because if we are putting up any of these two values like plus of 2 or minus of 2, then the denominator becomes a 0 and it becomes undefined. So for this relation, for this rule, we do have a constraint. The constraint is that we cannot use this one, right? This value. Similarly, for a domain of y equivalent to x minus y, this part, right, is a set of the real numbers. If I need to have a set of real numbers other than equal to 1, since any value of x less than 1, the root radical has a negative radicand, right? So we do have various restrictions while we move for these kind of domains of functions. Fine. Now I do have a few examples. Some of the examples are that you need to find out which of the relations describe a function, right? We know the definition of function very well. Now we do have an example at a, b, c and d. Now clearly by seeing here we can say that a and b is a function, whereas a and b is a function, whereas c and d is not a function. Why? Because a and b have fixed values. For any particular x values, they do have same or different y values. That means they map with only one value of x. Let us see here. Yeah, the equations a and b produce exactly one value of y for each value of x. Hence the equations a and b describes a function. Whereas in case of y less than x, it is not true, because here in this case we can have certain ordered pairs where I can have same x values, right? Similarly, for the case of x equal to y square also, I can have two ordered pairs like 4 comma 2 and 4 comma minus 2. In this case again, x value of 4 and x value of 4 remains the same. This thing doesn't makes this as a function, right? Now it's a very simple one. Function notation. Let's say I do have y equal to 5x minus 1. Then I can denote this y as f of x. I'll be substituting the values of x. Like for example, x equal to 2, then f of 2 becomes 5 into 2 minus 1. That means the value is 9. The value becomes 9. For x equal to 3, it becomes f of 3 and the value becomes 14. Right? So likewise we are talking about this. Now since the value of y depends on the value of x, then y is called as the dependent variable and x is called as the independent variable. Fine. After this, these are some of the parts which I'd like to give you a brief idea about. I have skipped the theoretical parts till now and I have talked about the problematic areas, I mean the problem solving areas, right? Now here you have a very good idea about the 8 puzzle problem. What is its state space? What is its initial state? What is its goal state? I've already talked about by using an example in my previous lectures, right? And the action that we take up are the blank moves. Hence I'm not going to move any I'm not going to talk any further on this. The transformations that takes place are on the basis of the blank moves: right, left, up and down. The solution is the optimal sequence of operators, right? For n-queen problem, I also know, we have already discussed it in the class also. We know what is the state space, right? We know what is the initial state, the goal state, the operators or the actions, right? And the solutions, that means one solution, the cost is not considered. Now since we haven't considered the costs, so here we'll be introducing something that you have gone through previously many a times in your algorithm part as well as in your data structure part. That means the completeness, the time complexity, the space complexity and the optimality. Now these things I'm not going to discuss about because you have to go through the theoretical concepts of the internal factors, the external factors, the time and space, the size, the speed and the quality. In case of external factors, you have to just go through these theoretical concepts, right? Now you have to go through the measure of the resources in terms of the time and space, the simple big O notation. You have gone through these things many a times previously also. There's much more description of the big O notation. All right, big O notation of an algorithm, how we do compute it you know it previously, right? We have talked about the performance complexities. These are the various complexities, and even more that you know very well, right? Now, these are simply the, the growth functions, right? You do have these. You have to go through all these things just once. And then you do have this curve, the growth rates, right? The various complexities. You have to go through them. Just you have to skim through this part, right? Then comes the various data structures. This thing also you have gone through, like the tree structure, in which you do have the branches. You can have the inverted tree with the root above, the binary tree. You know all these things. Like I'm having a tree here. I move down from the root. The root is at the 0th level. Then the next one, B and C, is at the first level, and then at the second level, these things are there. These are called leaf nodes. You know all these things. The properties. The special case of a tree is a graph. You know what is a root node. You know what is a parent. Then the child nodes. You know what is a leaf node, right? You know what is the depth. You don't have to go through this cognition part. You can skip it off for the time being, right? You can skip it off for the time being. Then you can again come up to the stacks and queues. You have got all the ideas about stacks and queues previously also. In your data structures, that means last in first out, or first in first out, right? Then in case of stacks, what you do is we perform the operations of the push and pop. This is how we do it. You have an idea of it. Then in case of queues, what you do is we perform deletions and insertions from the front and from the rear, right? It somewhat looks like this. A queue somewhat looks like this. This is the front part of it. This is the rear part of it, right? Then in case of search, I have already gone through what a search is. You'll be getting a tree out here. A tree-based search, we do have the various nodes, and this N and J are the goal nodes. How we are going to go through it? We can go through it by using DFS as well as by using a BFS model, right? We have already discussed the BFS and DFS in terms of graphs. Here we'll be seeing it for trees. Trees are very simpler as compared to graphs. All right. Search algorithms, we have gone through what are the search algorithms, the heuristics, not really intelligent. Then we have talked about uninformed searches and informed searches. We've talked about the informed searches and uninformed searches, right? And yes, these are the algorithms I'll be talking about separately in other lectures, right? Yes, again they're talking about blind, exhaustive, or brute force searches. This diagram I'd ask you to go through once, right? It doesn't have any value unless we go through all these algorithms one by one. We do have the uninformed searches and the informed searches under the category of the search algorithms. The DFS we have gone through, the BFS we have gone through, CFS we haven't, then depth limited, and IDDFS, that means iterative deepening depth first search, we haven't gone through. Generate and test we know theoretically. Hill climbing we have to go through, and all these things I'll be talking about, right? Well, this is a search space in case of a graph with the start and the goal state, right? Formal statement, exclusive lectures were there previously during our semester time, right? I'll not be going through all these things again. Now here, the search notations. This is the part on which I had a separate lecture, right? FNHN and GN. We have talked about this in our previous lectures. I'm just going through all these things and I'm revising, and I'm in a way connecting the parts that I have already taught you and the intermediate theoretical parts that I haven't talked about, right? These are things we have gone through, the G gap, H gap. right? The estimation of the heuristic function we have gone through. The control strategies, the forward search, the backward search, the data directed, the goal directed, right? We have gone through all these things in my previous lecture, right? I've given you these examples also in my handwritten notes. I've talked about chaining. Now these are the parts on which I do have exclusive lectures. We do have the inference rules, the deductive inference rules, the forward chaining. I've already talked about all these things. I'm just joining them off, right? The forward chaining example, then the forward chaining a particular problem case. We talked about the solution, and the other easier solution that I provided in my handwritten note. You have to refer to that lecture, right? Backward chaining, again, we have gone through all these examples previously. I have particularly talked about these problems in a exclusive lecture. This one also, all right. The exhaustive searches, previously we have talked about the graph cases for the BFS as well as that of the DFS in the class. All right, these are just the theoretical descriptions of the BFS and the DFS. Again, we do have these explanations. I'm not going through them. I'll be talking about IDDFS, or depth first search with an iterative deepening, or IDDFS we call it. Now here comes one more thing, that is the depth first search for a tree. So DFS for a tree will be somewhat like I'll be traversing from A to B, and then from B to D, and then from to E to H to L, M, N. So if I'm supposed to go to the goal node, that is N, or to J, or in fact the whole of the DFS for this tree would be A, B, D, E, H, L, M, N, likewise, right? L, M, N, I, O, P. This is the solution for it, right? The positions of the backtracking, right? You have to see DFS algorithm. I have already said it in the class. The BFS algorithm. In case of BFS, what we do is we do a level-wise search. We go for the 0th level, then the first level, then the second, the third, and the fourth. So I'll be moving in a raster scanning technique: A, B, then C, then D, E, F, G. Likewise, we'll be going, and this is the solution for that. We are having a solution out here, right? So this is again the algorithm for the BFS. This is a simple comparison of the DFS and the BFS. This is a theoretical part. You have to precisely go through them, right? These are comparison of the features of BFS as well as DFS. Then heuristic search techniques. Many times I have talked about them, right? Then the characteristics of heuristic search. These are simple theories. You have to go through them, right? Yes, from here onwards, I'll be discussing on a separate lecture. Thank you so very much.